Hello everyone, today we're looking at the distance formula. Because in geometry we have segments, and segments often have length, then there are many times when we want to calculate that length. Now we're going to be using distance calculations in two ways. One is, in a case like this, if we just have a number line, if you will, just a horizontal line, and then in the second case is if we have a slanted line, then we'll be using different formulas for those two instances. But we're taking it a step farther. We're not just finding the distance of the entire segment, but we're also going to be looking at finding part of the distance. What is a partial distance? And that's what this first goal is describing. We're going to find a point on a segment that partitions, or is a partial distance of the segment. So we'll be working with this idea first, and then we'll be getting to the more traditional distance formula that you've seen before, but we're going to increase the complexity a little bit by using not just numbers, but also variable coordinates as well. So that'll be a new topic that we'll get to in a moment. Here we're starting off with example 1, and it breaks this process down into 3 steps to make it a little bit easier for us. The goal here is really to find a partial distance, but before we can find a partial distance, we have to start with finding the entire distance, the entire length. And that's what part A is starting us off with. So in example 1, part A, find the length of the given segment. Here's our segment. Typically, the segment must have capital letters on the endpoints, and for whatever reason it's not labeled. So let's go ahead and put a capital A and a capital B on there. So we're calling this segment AB. What is the length of segment AB? We could just count, to be honest. Remember, if you start at one endpoint here, don't count that as a 1 because we haven't traveled anywhere yet. This is 0, and then as soon as we move to the next tick mark, that's a length of 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a length of 9. Okay, but I want to show you how we can calculate that with subtraction, because we defined distance a couple days ago in our notes, and we said that to find the length of a segment, it is the absolute value, because it has to be positive, it's the absolute value of the difference. That means it has to be a subtraction problem, and what we're subtracting are the values on the endpoints. And it doesn't matter which one is first or which one is second. So we have a value of -3 and we have a value of 6. So when we combine like terms inside the absolute values, we have -3 minus 6, that gives us -9. And then the absolute value of -9 is +9, and that matches what we counted. So you really do have two ways of answering that question. You can count, but that's a distance formula for just a horizontal line, just a value on the number line. This is now where we're getting into the partial distance. Let's take a look at part B. If you begin at the leftmost point of the segment, meaning we're going to start at A and travel to the right, but we're not traveling all the way to point B, we're only traveling 1/3 of the total distance. Alright, so what we're going to do is recognize that this value of 9, this 9 is the total distance, but we want to find a partial distance, and we're going to find a partial distance by using that total distance of 9. We want to know what point is 1/3 of the total distance. So 1/3 is the portion of means multiply, and we're going to multiply that with the total distance, and our total distance is 9. Alright, so what we're doing is we're taking the 1/3 of means multiply. It says what is 1/3 of multiply the total distance. The total distance is 9, and this is not our answer because this is just a partial distance. 3 is the partial distance that we must travel. Because the question is not asking what is the length, it's asking instead what point do you end up with. So here in part B it says if you begin at the leftmost point. So you have to start at A, and you have to travel across the number line the partial distance of 3. So that means we're going to count 1, 2, 3. That's the answer. They're asking us then, where do we end up? We end up at 0. So to fill in the blank, we place 0. That's the value on the number line we end up after traveling 1/3 of the total distance. Alright, let's try that again with part C. Here we have a different partial distance to calculate. In part C it says, what point is 2/3 of the total distance from the leftmost point? So again, we're starting at the leftmost point, we're traveling rightward, but how far do we go? We have to calculate that partial distance. So this tells you what to do. It says take 2/3 of means multiply, and you multiply that with the total distance. So 2/3 of means multiply, and we're multiplying that with the total length, and this will give us our partial distance. So 2/3 of 9 is 6. So 6 is not the final answer. 6 is the partial distance. So that's how far we're going to count along the number line. Now again, it tells us to start at the leftmost point. So we're starting at point A, and we're counting a length of 6. So 1, 2, 3, 4, 5, 6. So we traveled 6 units to the right, and we ended up at a value of 3. So what point are we at? We're at the value of 3 on the number line. So that's the concept of a partial distance. We're going to do that one more time with example 2, just to see that process again. Here's example 2. Again, part A says to find the length of the given segment. We could count, but instead let's just do our calculation. What is the length of segment GH? It is the absolute value of the difference of the values of the endpoints. So we have a -6 and we have a 4. So that means it's the absolute value of -10. So +10 is the total length. Again, we could have gotten that just by counting, but we need that number to then solve for the partial distance. In part B, the partial distance says, or the problem says, if you begin at the rightmost point of the segment, what point is 1/5 of the total distance? This tells you what to do. Let's multiply 1/5 times the total distance. So 1/5 of the total distance of 10. So that answer is 2, but another way to look at that is if you think of 10 as being a fraction of 10 over 1, remember, this is just review. When you are multiplying fractions, you multiply straight across. So top times top, and bottom times bottom. And then when you simplify that fraction, that's how we get the result of 2. So 2 is the partial distance. Alright, so which end are we starting at from? It says if you begin at the rightmost point. Okay, so we're beginning at point H. This time we're traveling 2 to the left. So I'm going to represent that by -2 because we're going leftwards. And we end up at 2 on the number line. So that answer is 2 on the number line. Here's one more. Part C. What point is 3/5 of the total distance from the rightmost point of the segment? So this tells us what to do. 3/5 of means multiply, and the total distance. So here's 3/5 times the total distance of 10. So again, let's multiply our fraction straight across. 3 times 10 is 30. 5 times 1 is 5. Reduce the fraction and we get 6. So 6 is the partial distance. Again, we're going to travel from the rightmost point. So starting at point H, count 1, 2, 3, 4, 5, 6. There we've traveled 6 to the left and we ended up at -2. There you go. So that's the first concept with using a kind of distance formula. It's not your traditional distance formula that you are thinking of. We'll get to that in just a moment. But this is how you can calculate a distance just with subtraction and the absolute values and a partial distance. Notice that this method of calculating the total length only works if it is a horizontal or vertical line. If it's a slanted line, well, then we'll have to use the distance formula. And let's talk about that next. So let's go to the next page. I'm skipping over example 3 here. I'm skipping over example 4. And we're going right to the distance formula. That's what you're thinking of with the distance formula. So we have two endpoints. And again, to keep the x's separate from each other, we're calling one x sub 1 and the other x sub 2. When we were looking at our midpoint formula, we were color coordinating these, and you could do the same thing here. I'll do an example where I'm also coloring the x coordinates, and notice how we bring those x coordinates together. And then with the y coordinates, those y coordinates are what are brought together. And this can be a handy strategy to make sure that you are combining the right numbers, because sometimes I find students will accidentally try to combine the wrong numbers together. You want to keep the x's together and the y's together. It reads, the length of the segment AB is equal to the square root of the quantity x sub 2 minus x sub 1, quantity squared, plus y sub 2 minus y sub 1, quantity squared. Here it says always round to the nearest hundredth. That means 2 decimal places, and that's if we have a number for an answer, but we won't always get numbers, and I'll show you what we mean in a couple of examples. Let's start off with the traditional formula for part A. What is the length of segment RT with endpoints at R is 3, 2, and T is negative 4, 3? Let's plot this. R is at 3, 2, so 3 to the right, 2 up, there's endpoint R. And T is at negative 4, 3. So from the origin, left 1, 2, 3, 4, and up 1, 2, 3. That's point T. Notice this is a slanted line. That means you cannot just count the distance. You cannot use the absolute value formula we saw on the previous page. No. If it's a slanted line, we must use this distance formula. Remember, with the bar, we're naming the segment. When we take the bar away from the letters, now we're talking about the length. And that's what you see set up here. In Algebra 1, you use D for distance. But in geometry, this is how we name the segments. So don't use D for distance, call the segment by its name. So this is the length of segment RT. So to color code these, again, we want to find the x coordinates of the ends. So that's going to be a 3 and a negative 4. Bring them together and we're going to subtract them. So we have 3 minus negative 4 quantity squared. And then find your y coordinates. We have a 2 and a 3. We have 2 minus 3 quantity squared. Now some of you might say, whoa, wait a minute, aren't your numbers backwards? Aren't you supposed to be putting that second point in front and the first point in back? Isn't it supposed to be x sub 2 minus x sub 1? Well, does it really matter which point we've listed first or second? Can't we switch them around? And we could have listed point T first and point R second. And the answer is no, it does not matter the order as long as you are consistent. So we could have, again, here's the x coordinates of 3 and negative 4. We could have said negative 4 minus 3 quantity squared. And then for the y coordinates we have a 2 and a 3, so 3 minus 2 quantity squared. So it doesn't really matter whether the negative 4 is in back or in front, as long as you are consistent with how you set this up, and it'll work out just fine. So continuing with my original setup here, remember when you're subtracting a negative, that turns into adding a positive, so 3 minus negative 4 is 3 plus positive 4. That will give us a result of 7 that we'll have to square. The y coordinates are 2 minus 3. That gives us a -1 that we have to square. And so when we do that, we end up with 49 plus +1. So be very careful here when you square a value. It always becomes positive. And so we end up with square root of 50. So we could reduce the radical, but that will be for a future topic. Here we're just rounding it to the nearest hundredth, so I grab my calculator and let's do a quick review on rounding. If I were to type this into my calculator, you will see a long string of decimals that looks something like this: 7.07106778. Alright. If we want the nearest hundredth, that means we want just 2 decimal places, and the question is, how do we round? So you always have to look at the third value to see how it impacts that hundredth place. Remember, if that third value is 5 or bigger, then we would round up that 7 to an 8. Otherwise, we keep it the same. So our final answer is just 7.07. That's our approximate answer. Let me adjust the camera here. I'm going to skip over part B. That's the same idea, using numbers to find the distance. It gets different in these last two examples when we take the numbers out and we replace them with variable coordinates. Here in part C it says find the length of JK with endpoints of, J is located at 4C, 0, and K is located at C, 0. That seems very strange because we're so used to using the distance formula with numbers, and we take the numbers out, we have variables now. How do we work the distance formula with that? Also, we can't diagram a picture because we don't know where C is located. And that's okay. We can still use the distance formula, and we'll be doing this a lot more in a future unit. This is more of an introduction. So let's get this set up. Alright. The length of JK is the square root of, find your x coordinates there in front. So we have a 4C and a 1C. We need to subtract those. So 4C minus 1C quantity squared. Find your y coordinates. They happen to be zeros in this case. We'll subtract those as well and square the result. So that's the setup. So what we have here is an expression with like terms. So inside the parentheses, we need to combine those like terms. 4C minus 1C is 3C. And we'll square that on the next step. The zeros just cancel out. I hope you're comfortable with that. 0 minus 0 is just 0. When you square 0, it's still 0. So that just disappears. So this is what we have to work with. So keep in mind that when you have an expression squared, what's really going on behind the scenes is this. Because you have an exponent of 2, that means you really have 2 of these things. We usually just do this in our head. We don't write it down. But just so you know, that's what's happening. So when you multiply those together, you end up with 3 times 3 is 9, and C times C is C squared. We usually jump from this point to this point and do that in our heads, but that's how we get the 9, and that's how we get the C squared. Now, if we have perfect squares, then we do want to simplify. Can you take the square root of 9? Yes. Can you take the square root of C squared? Yes. And that's the answer. That's the length. So even though we had variable coordinates in the endpoints, we can still calculate the length. And you notice we still have variable coordinates for the length, or a variable result for the length. We have an expression for the result, and that's the answer. Whatever C is, we don't know, but we know that the distance between those would be 3 times the value of C. This problem is a little bit easier because of the zeros. The zeros dropped out. But let's take it to the next level and take a look at a problem where they don't drop out quite so nicely. Here's our last example for today. What is the length of segment ME with the endpoints of point M, which is 5D, 2D, and point E is 9D, 1D. Alright, let's set this up. Here is segment ME. create my square root sign. Let's find those x-coordinates. We have an x-coordinate of 5d and 9d. I'm going to subtract those, so we have 5d minus 9d quantity squared. The y-coordinates are 2d and 1d. So again, we need to subtract those as well. 2d minus 1d quantity squared. So inside the parentheses, you see we have like terms, and that means we need to simplify inside those parentheses. So here we have 5d minus 9d. That gives us negative 4d. We'll square that on the next step. In the next set of parentheses, we have 2d minus 1d. That gives us 1d. And we'll square that on the next step as well. So when we are squaring, remember, that's what we saw up here. That means you have two of these expressions that are being multiplied together. In the previous example, we had a 3c quantity squared, so that meant 3c times 3c. So think about our example now. We have a negative 4d quantity squared. That means you have two of these. You have a negative 4d times negative 4d. So a negative 4 times a negative 4 gives you positive 16, and a d times d gives you a d squared. There's the plus sign. And now here you have a d squared, and that's pretty much it. You have a d times d, and that gives you d squared. So when you take a look at this, notice again we have like terms. 16d squared plus 1d squared combined to give us 17d squared, and that's all under the radical. And you might think you're done, but we're really close. We're not quite done. The next thing to do is to simplify the radical if possible. In the previous case, 9 was a perfect square. We could take the square root of 9 to get 3. But in our current example, 17 is not a perfect square. 17 will stay under the radical. Then when we take a look at the variable, we have a d squared. That is a perfect square. We can take the square root of d squared, and we get just d. So that's the final answer. It's a root 17 times d. You'll notice I did not turn that into a decimal value in this case. When we are working with variable coordinates, we tend to leave it in its precise form as opposed to its approximated form like this. And that's it for our notes today.